This lecture is going to cover Chapter 9, which is about confidence intervals. Let's return to the basic question of statistics. So we have some population, and there's a parameter that we would like to know about that population. So it could be what percentage of people are going to vote for a particular candidate. For one reason or another, we cannot do a census. Usually we don't have the resources or the time to interview everybody. If we could interview everybody, we would then know the parameter, but we can't do that. So instead, we gather a sample of units in that population, measure them, and we form some statistical estimate. So we've seen a lot of these estimates in this class. One is x bar, the sample mean. Another is p, the sample proportion. T hat would be another example of a statistic, as would S, the sample standard deviation. Once we have an estimate, our next question is, how good is it? Now, there are two general approaches. There are biases and there's sampling variation. We're going to talk about biases next time. This lecture is really going to talk about the sampling variation. So there are really two ways to answer that question. Two subways within this area of sampling variation. In essence, we want to know how stable is our estimate. So the answer to this is going to be confidence intervals and margins of error. That's what Chapter 9 is all about. The other way of addressing this question of sampling variation is that we'll often ask a question, what can we say about the parameter in relation to other numbers? So is it smaller than some constant? Is it smaller than another parameter? For example, if we need to have a certain click-through rate for an ad to be profitable, that's a constant. We want to know, is the estimated click-through rate greater than that constant? As for comparing to other parameters, we're going to have a question such as, is purchase intent of segment A greater than or less than the purchase intent of segment B, if we're making, say, a targeting decision? All right. These questions we're going to answer come Chapter 10. So the first bullet is all about Chapter 9, the second is Chapter 10. What we're really asking whenever we address these questions of sampling variation is this very profound question, the most profound question of the course. If we draw on a different sample, would we come to different conclusions? All right, let's move on to confidence intervals. So we're answering how stable is the estimate. This slide tells you everything you need to know about confidence intervals most of the time. Now, there'll be instances where this slide doesn't apply, and we'll get to those later. But in my experience, most of the time, this is what I'm doing. So let me make this a little bit more precise. Whenever you're in this situation, you've got a random sample from some large population. So that's often something that we assume. And let's say that the sampling distribution is approximately normal. So what does that mean? Well, the sample size should at least be 40 or so and sufficiently large for the central limit theorem to apply if the population distribution is not normal. Okay, so if it's skewed, watch out. If there are outliers, watch out. You're going to need a much larger sample size. But other than that, if you have samples of 40 or so, then you're probably good to go on this slide. So those are the conditions for using this slide. Definition 1. The margin of error is simply 1.96 times the standard error of whatever you're estimating. Now, a lot of people and a lot of times will round that 1.96 to 2, which brings us back to the empirical rule. All right, so remember we said 2 standard deviations. All right, well, it's really 1.96, but we round that to 2. So that's the first definition. Second definition, a 95% confidence interval for some parameter mu is simply x bar plus or minus the margin of error. So in essence, you're going 2 standard deviations away from the statistic. Now, let's try to understand the rationale for doing this. Let's go down to this literal interpretation. This first line is really just stating the empirical rule. So what it's saying is the chance of observing a random variable x bar that is sandwiched between its mean minus 2 standard deviations and its mean plus 2 standard deviations is 95%. So why don't we go draw that? I'm going to go over to the sketchbook, and here is a nice normal curve. So provided we have a normal curve, here is your statistic. It could be x bar. All right, so if this is your mean, and we go out 2 standard deviations, all that first line is saying is that 95% of the area lies within 2 standard deviations of the mean. So we've been talking about that since about the second or third week, probably the second week when we talked about the empirical rule. So 95% of the probability sits in there. Now we're going to do some algebra on this that makes it a little bit weird. So what we're going to do is add, subtract a mu from all parts of this inequality, subtract an x bar from all sides, and you end up with this next line. So it says if you take the estimate minus 2 standard deviations and the estimate plus 2 standard deviations, mu is sitting in the middle. And so that's what this 95% confidence interval business is all about. If you think about it, I'm going to observe an x bar. I don't know where it is on this graph. Let's just say that my x bar is right here. This is what I observed from my sample. All this is saying is if I take this x bar and I go 2 standard deviations out, so that's 2 standard deviations out in one way. Let's go 2 standard deviations out the other way. This is your 95% confidence interval. So do you see the difference? We're adding 2 sigmas, and again, subtracting 2 sigmas from the estimate x bar rather than from the parameter, which is what we've been doing all along. The reason that we're doing this is we don't know the parameter. All we know is x bar and the margin of error. So think of this as a give or take number. What that means is this 95% confidence interval that I've just established right here gives us a little window. So here's a window where we think the true parameter lies, and sure enough, the parameter does lie within that window. All right, so it gives us a little window where we think the parameter lies. Let's now do a simple example. So the owner of some record store wants to know the average age of his customers. He draws a random sample of 87 customers, asking them their ages. The average age was 20. Standard deviation was 5. So we're to find the margin of error and a 95% confidence interval. Well, let's start by identifying what we've been given. So 87 is n. X bar is 20. That's the average age from the sample. And S sub x, which is called the sample standard deviation, is 5. The margin of error then is simply plus or minus 2 times sigma over root n. So the margin of error is about plus or minus 1 year. You can attach the year units to this. The confidence interval then is going to be 20, so the mean plus or minus the margin of error, which gets us to a window of 19 to 21. So I told you earlier to think of this as a give or take. The margin of error is a give or take number. We know the age within about a year is a way that we could say this. We think the true parameter is probably somewhere in this 19 to 21 range. Now, I'd like to draw your attention to an interpretation that is wrong. So a lot of people and a lot of books will interpret this as follows. They'll say there's a 95% chance that the true average age of his customers is between, say, 19 and 21. This is it's kind of picky, but that statement is not correct. Here's the problem with it. There's a 95% chance that the true average age, okay, so it sounds like we're making a probability statement about the true average age. The problem with this is the true average age is not a random variable. The true average age is a parameter. So we could find this true average age with a census. Go out and do a census, we would know mu, the true average age. If we drew another census, we would get exactly the same parameter. So exactly the same number for that parameter. So my point here is that it's not a random variable, therefore we cannot make random probability statements about it. So what is random? The thing that is random is the sample that we happen to draw, which then gives forth an x bar. So x bar is the random thing which results from that random sample that we draw. So we need to find a way to make a probability statement about the thing that is random rather than attaching a probability to a parameter, which makes no sense. So how do you do this? Well, the next page gives us the interpretation that the New York Times gives for a confidence interval. In particular, let me draw your attention to this bolded paragraph up here. So in theory, in 19 cases out of 20, so let me translate 19 cases out of 20. 19 cases out of 20 is 95%. So in theory, 95% of the results based on such samples. So notice that we're now talking about 95% of the time these results from a sample. We're talking about the thing that's random, which is the results, x bar, or p in this case, they're estimating percents in this New York Times article, will differ by no more than 3 percentage points in either direction. So those 3 percentage points in either direction is plus or minus 3%. That's the margin of error from what it would have been obtained by seeking out all American adults. So this from what would have been obtained by seeking out all American adults is the parameter. If we could have done a census, i.e. seek out all American adults, that would give us the parameter. So let me draw a picture for you that I think makes this clear. So let's say that here are possible values of our parameter. And this is the true parameter right here. So here is pi in the case of that New York Times article where we had a percentage that we were estimating. Now, the way to think about this is you've drawn a sample and you've estimated a p. So I'm going to say that that is p. And we've computed a confidence interval for that p. So here is that confidence interval. So here is a window where we think the true parameter lies. Now, that's what we've done, and sure enough, the parameter falls in there. What you want to picture is the possibility of being able to repeat the sampling procedure again. So let's say that New York Times article interviewed about 1,200 people. If we could do this again, well, we would get a different P since we talked to different people. So let's say here is a P from that second sample. Here's the confidence interval. Now let's do it again. We get another P, here's the confidence interval. You get another P, here's that confidence interval. Get another P, here's that confidence interval. Get another P, here's that confidence interval, and so forth. So we could repeat the sampling procedure, and occasionally we would get a sample like this, giving a confidence interval like this. So notice this confidence interval does not cover the parameter. What confidence intervals tell us is that this will happen one time out of 20. One time in 20. All right, we can say that with great precision. So 19 times out of 20, the confidence interval covers the parameter. One time in 20 it doesn't. Okay, so that's how the New York Times interprets it, and that is correct. Okay, let's talk a little bit about proportions. Since the New York Times did it, there's nothing really new here. It's just p plus or minus 2 times the standard error. You compute the standard error as you did back in Chapter 8. Margin of error, again, is same as before. Okay, one more issue. We're using the 95% confidence interval so far, but we need not always do so. Most of the time in practice it's 95%, but in theory it would be possible to compute a confidence interval with a different degree of confidence. Here are some commonly used confidence levels. So maybe we want to use a 90% confidence interval. That would indicate that 9 times out of 10 that confidence interval would cover the true parameter if we could repeat the sampling procedure. 99% confidence intervals, so that would mean there's only 1 chance in 100 that you'd get an unlucky sample where the confidence interval would not cover the parameter. To compute these other confidence intervals, what you're going to do is use different z-values. So you're going to use 1.645 for a 90%, 2.576 for a 95%. Okay, let's do a little example now. I used to follow impeachment polls, and that's roughly when I made this slide. On December 16, 1998, there was an impeachment poll done, and they asked people whether they thought Clinton should be impeached. There were 204 shoulds out of 510 adults. Okay, so what this indicates is that 40% of the sample thought that Clinton should have been impeached. That's a statistic P. Now, I've asked us to find a 90, 95, and 99% confidence interval, and here are those intervals. So notice the only difference between them is I use a different z-value. For the 90%, we're going to use 1.645. For the 95% confidence interval, we're going to use 1.96, and for the 99, 2.576. Notice what happens to the intervals. So the intervals get bigger. With the 90% confidence interval, it's 40% plus or minus, call it 3.5%. So here's 40%, and you go out 3.5%. For 95, you have to go out 4%. So the interval gets a little bit wider. And for 99, you're going to go out 5.6%. So here's 99%. And that ought to make sense to you that if you want to have a higher chance of this interval covering the truth, well, then you better make the thing longer. So that ought to go with your intuition. All right, I'm going to make a separate video for these problems, but you might want to try them on your own first. So in a subsequent video, I will do problems 1 and then 2